Energy resources can be renewable or non-renewable. Coal is a non-renewable energy resource. Name two other non-renewable energy resources. So coal is one of three fossil fuel, and a fossil fuel is one type of non-renewable energy resource. The other two are oil and gas. You also could have said nuclear power, which is another type of non-renewable energy resource, but you only need two to get full marks. Wind turbines are used to generate electricity. Figure 1 shows how the power output of a wind turbine changes over one day. So you can see that there's power output in megawatts on the y-axis and time in hours on the x-axis. So for each time, you can find the corresponding power output. A wind turbine does not generate electricity constantly. For how many hours did the wind turbine generate no electricity? So power is work done divided by time. So if no electricity has been generated, no work has been done, so the power output is going to be 0. So that means this time period is the time period where power is 0. From the graph, we can see that this period here is the period where the power output is 0. So this point is 14 and this point is 18. That means our final answer is 18 minus 14 equals 4. 4 hours. Electrical power is transferred from power stations to the national grid. What is the national grid? So we know from our definition that the national grid is a system of cables and transformers that connects consumers to power stations. So we need to find which one of these three statements most closely matches our definition. So is it a system of cables and pylons? No. So while cables are part of the system, pylons aren't. So I don't think this is our correct answer. Is it a system of cables and transformers? Yep, so far that matches our definition. So it might be this one. Is it a system of cables, transformers and power stations? Okay, well, power stations and consumers are what are connected by the national grid. They're not part of the national grid themselves, so that means this last one's incorrect too. So the middle one is the correct answer. An island has a large number of wind turbines and a coal-fired power station. The island needs to use the electricity generated by the coal-fired power station at certain times. Choose one reason why. Is it because wind is a renewable energy resource? While this statement is correct, wind is a renewable energy resource, that doesn't explain why the island would need to use a coal-fired power station, so this can't be our answer. Is it because wind turbine power output is constant? This statement is incorrect. Wind turbine power output is going to be much greater when it's windier compared to when it's less windy, so this can't be our answer. Is it because the power output of wind turbines is unpredictable? This statement is correct, and it would also explain why the island would need to use a coal-fired power station, so it's looking like this is our answer. Is it because the fuel cost for wind turbines is very high? No, this is incorrect, because wind turbines don't need fuel. So the third one is our answer. A wind turbine has an average power output of 0.60 megawatts. A coal-fired power station has a continuous power output of 1,500 megawatts. Calculate how many wind turbines would be needed to generate the same power output as one coal-fired power station. So the answer to this is just going to be the average power output of the coal-fired power station divided by the average power output of the wind turbine. Both the units are the same, so we can get our answer of 2,500. So 2,500 wind turbines would give the same power output as one coal-fired power station. It is important that scientists develop new energy resources. Choose one reason why. Is it because all energy resources are running out? Well, by definition, renewable energy resources are not running out, such as wind power, so not all energy resources are running out. Is it because all energy resources are used to generate electricity? This statement is also incorrect. For example, fuel in cars is not used to generate electricity. Is it because most energy resources have negative environmental effects? This statement is correct, and it also explains why scientists need to develop new energy resources, so it's correct. Figure 2 shows a student before and after a bungee jump. The bungee cord has an unstretched length of 20 meters. We can see the student before the bungee jump and then the student at its stationary point. We know that this is also its lowest point, which means it's the point with the greatest extension. We can see unstretched length of 20 meters plus some extension. For safety reasons, it is important that the bungee cord used is appropriate for the student's weight. Give 2 reasons why. So, one way to approach this question is to think about a really extreme circumstance. So, imagine that an elephant was using the same bungee cord as the student. Why would this be unsafe? If an elephant used this bungee cord, we know that the extension would be much greater, and this might be unsafe. We know this is true because of Hooke's law, F equals kx. With a greater weight or a greater force and a constant, we know that the extension must be greater. So the first risk of using a non-appropriate bungee cord would be extension too great. Another thing we can imagine, say if an elephant was using the bungee cord, is the cord might snap. The student jumps off the bridge. Complete the sentences to describe the energy transfers. Use the answers from the box. So we have 5 key energy related terms and we've got to fill in the 3 blanks. Okay, so before the student jumps from the bridge, he has a store of what energy? So when the student is standing on the bridge, he's going to be at a height, and gravitational potential energy is the energy of something at a height. So we know straight away that it's probably going to be that answer, but we can check the other ones just to make sure. Elastic potential energy is the energy stored when an object is stretched or squashed. So nothing is being stretched or squashed, so it's not going to be this one. Kinetic energy is movement energy, and when the student is jumping on the bridge, before the student jumps from the bridge, he's going to be standing still, so it's not going to be kinetic energy. And sound energy is not a store, and a thermal energy store refers to the movement of particles, so it's not going to be either of those two. So it will be gravitational potential. When he is falling, the student's store of what energy increases? So when the student is falling, his height is going to be decreasing, so its gravitational potential energy will be decreasing, so it's not going to be that. Again, for the same reason as before, it can't be elastic potential energy, or sound, or thermal, so it must be kinetic energy. We know this is true because the student goes from standing still to falling with a speed, so the kinetic energy will increase. When the bungee cord is stretched, the cord stores energy as what energy? Again, elastic potential is the energy stored when an object is stretched or squashed. So, as the bungee cord is stretched, that is how it will store energy. At the lowest point in the jump when the student is stationary, the extension of the bungee cord is 35 meters. The bungee cord behaves like a spring with a spring constant of 40 newtons per meter. Calculate the energy stored in the stretched bungee cord. use the correct equation from the physics equation sheet. Okay, so we need to find out our equation, and the values we have are, we have an extension and we have a spring constant, and we need to find energy stored. So if we look at the physics equation sheet, we can find the equation E equals half kx squared, and we have all the information we need. Our units don't need to be converted, so we can sub the values straight into the equation. If we type that into our calculator, we get 24,500 joules. We're asked to give the answer in joules, so it's 24,500. An electrical circuit is shown in figure 3. We can see the circuit has a battery, two fixed resistors of 20 ohms and 10 ohms, and a 0.4 amp current. The current in the circuit is direct current. What is meant by direct current? So you might already know the definition of direct current, but if you don't, you can work out the correct answer through the meaning of the word direct and the circuit given. So is it current that continuously changes direction? So this doesn't really sound direct, and it also doesn't really sound like what's shown in the diagram. So I wouldn't think that would be the answer, and you'd be correct to think that, because that's the definition of alternating current. Is it current that travels directly to the component? So this does sound very direct, but if you think about it, if there's a current flowing directly to the 20 ohm resistor, it would look like this, and if there was a current going directly to the 10 ohm resistor, there'd be another current like this, and that is impossible. In a series circuit, the same current flows through each component, and there definitely can't be two opposing currents looking like this, so it's definitely not this answer. Is it current is always in the same direction? Yeah, so that does sound a lot more direct than the first one, and that does make sense, so this must be our answer. And we would be correct, because that is the definition of direct current. The equation which links current, potential difference and resistance is potential difference equals current and resistance. Calculate the potential difference across the battery in the circuit in figure 3. So using this equation to find the potential difference, we need to find the current across the battery and the resistance across the battery. In a series circuit, the current is the same everywhere, so if it's 0.4 amps here, it's also going to be 0.4 amps across the battery. The total resistance of two or more components in series is equal to the sum of the resistance of each component. So the total resistance is going to be 20 ohms plus 10 ohms equals 30 ohms. We can put these values back into our equation to find potential difference. 0.4 amps times 30 ohms equals 12 volts. The equation which links current, potential difference and power is power equals current times potential difference. Calculate the power output of the battery in figure 3. Give your answer to one significant figure. So to find the power output across the battery, we've got to find the current across the battery and the potential difference across the battery. From our last question, we remember that the current across the battery is 0.4 amps, and we also worked out that the potential difference across the battery was 12 volts. If we put this into our equation, we get an answer of 4.8 watts. However, the question asks us to give our answer to one significant figure, and this is currently two significant figures. So our final answer is 5 watts. Two students investigated the change of state of stearic acid from liquid to solid. They measured how the temperature of stearic acid changed over 5 minutes as it changed from liquid to solid. Figure 4 shows a different apparatus the two students used. You can see that student A used a digital data logger and student B used a thermometer. Choose 2 advantages of using student A's apparatus. Tick 2 boxes because this question's worth 2 marks. Is it because student A's apparatus made sure the test was fair? So, a fair test normally refers to control variables. For example, in this experiment you would need to make sure the temperature of the room was constant. A fair test doesn't normally refer to how you would measure a variable, so I don't think that's the answer. Is it because student B's apparatus only measured categoric variables? Okay, so there are 2 types of variables, categoric and continuous variables. Temperature is actually a continuous variable because it can take any value on a range. You could have 74.2 degrees or 74.3 degrees or anything in between. Both student A and student B are both measuring continuous variables, not categoric variables, so that's incorrect. Student A's measurement had a higher resolution. So the resolution of an instrument refers to the smallest change in a value that can be detected. We can see that the smallest change in value that can be detected from student A's data logger is 0.1 degrees C, because we can see it measures to 1 decimal place. However, the thermometer is only graduated to 1 degree C, so that is the smallest change that you can see. Because the smallest change in value that can be detected for the data logger is much smaller than for the thermometer, it means it has a much greater resolution. So that means this statement is correct, and it's also an advantage of using student A's apparatus, so this should be one of our answers. Student B was more likely to misread the temperature. So with student A's apparatus, the data logger will display the value and you just have to write down what it says. So that's pretty much impossible to misread. However, with student B's apparatus, you have to look at the line and make your own judgment as to which value it's closest to. Also, what you see depends on what angle you're looking at it from. So if you're not reading the thermometer from eye level, you might also misread it. So this statement is definitely correct, and it's also an advantage of using student A's apparatus. So our 2 answers are the bottom 2. Student B removed the thermometer from the liquid each time he took a temperature reading. What type of error would this cause? Would it be a systematic error, a random error, or a zero error? Okay, so a systematic error is one which is consistently above or below the real value by a set amount each time. If you take out the thermometer before reading, the reading will be slightly closer to room temperature each time. How big this difference or error is, and whether the new reading is slightly above or slightly below the real value of the temperature of the liquid, is going to depend on what the real value of the temperature of the liquid is. It's going to depend on whether the temperature is hotter or colder than room temperature. So that means it's not going to be consistently above or below the real value by a set amount. So it's not going to be a systematic error. So a random error is exactly what it says, random. So this could be caused by a human error, a faulty technique in taking a measurement, or faulty equipment. And the key is it doesn't have to be the same every time, like a systematic error. So this does sound like what student B will get. So this is probably our answer. Is it a zero error? A zero error is caused by faulty equipment that doesn't reset to 0 properly. A 0 error with a thermometer is really unlikely. It's much more common in things like scales. So this probably isn't our answer. And we'd be right because this is the correct answer. Student A's result is shown in figure 5. You can see there's a graph of temperature against time, so you can find the temperature for any time. What was the decrease in temperature between 0 and 160 seconds? The temperature change during this period is going to be the temperature at 160 seconds minus the temperature at 0 seconds. We can read from the graph that the temperature at 160 seconds is 55.6 degrees C. We can see that the temperature at 0 seconds is 64 degrees C. So the temperature change is 55.6 minus 64 equals minus 8.4 degrees C, which means the temperature decrease is going to be 8.4 degrees C. So this one is the correct answer. Use figure 5 to determine the time taken for the stearic acid to change from a liquid to a solid. We know from earlier on in the question that this point here must be a liquid, and this point here must be a solid. However, we know that this whole time period, the whole 1200 seconds, is not the time taken for it to go from a liquid to a solid. This time period also includes some time where the liquid decreases in temperature and the solid decreases in temperature. We know when something changes state, there is no change in temperature. So the time period we're looking for is the time period where there is no change in temperature. So that is from this point here to this point here. So the time period is from 160 seconds to 900 seconds. So our final time period is 900 minus 160 is 740 seconds. Calculate the energy transferred to the surroundings as 0.4 kilograms of stearic acid changed state from a liquid to a solid. The specific latent heat of fusion of stearic acid is 199,000 joules per kilogram. Use the correct equation from the physics equation sheet. The specific latent heat of fusion is the energy transferred to change the state of 1 kilogram of a substance from solid to liquid or liquid to solid without changing its temperature. The equation that represents this is energy equals mass times specific latent heat diffusion. So we can plug in our values to find the energy transferred. 0.4 kilograms times 199,000 joules per kilogram is 79,600 joules. We get 1 mark for this calculation here and 1 mark for our final answer. After 1200 seconds, the temperature of the stearic acid continues to decrease. Explain why. So, if we use the graph, we see that at 1200 seconds, the temperature of the stearic acid is 53.2 degrees C. This is much hotter than room temperature, which is normally about 22 degrees C. We know that in general, Heat is transferred from hot objects to cold objects until they are the same temperature. So we know that heat is going to be transferred from the hotter stearic acid to the colder surroundings until the stearic acid reaches room temperature. So this is why the temperature of the stearic acid continued to decrease. This question is worth two marks, so we need to write 2 points. The first one is that stearic acid has a higher temperature than the surroundings. This gets us the first mark. Then we need to say that the temperature of the stearic acid will decrease until it's the same as the surroundings. This gets us our second mark. A student wants to investigate how the current through a filament lamp affects its resistance. Use the circuit symbols in the boxes to draw a circuit diagram that she could use. So we know that we need to know the current and the resistance through a filament lamp. So to find the current, we can just put an ammeter in series. There's no direct component that we can use to measure the resistance, but we can use V equals IR. So V divided by I is resistance. And to find the potential difference through the filament lamp, we need a voltmeter in parallel. Of course, we also need a power supply, and the only one we have here is a 12-volt battery, so that's what we'll use. If we connected the circuit just like this, there would be no way to change the current or the potential difference across the filament lamp, so we wouldn't be able to find a relationship between resistance and current because the values wouldn't change. So to make the values change, we need to include a variable resistor. So this is the circuit we need so we can connect it all up. Describe how the student could use her circuit to investigate how the current through a filament lamp affects its resistance. So we need to find pairs of values of current and resistance and see how when one changes, the other changes. So we need to be able to find current and resistance. We can use an ammeter to measure current. We also need to use a voltmeter to measure potential difference across the filament lamp. So that we can calculate resistance using R equals V over I. So this is how we can find current and resistance, but we also need to describe how we're going to change those values. To change the current, we need to change the resistance of the variable resistor. So we can change the current through the filament lamp. There's one more point we should make, and that's if we're investigating something, we need to make sure that we're using a large range of values so that any conclusion we make is valid. So the resistance needs to be calculated over a large range of currents, so conclusions are valid. So this last point just makes sure we find all of the patterns. So say there's a different pattern when the current is going in the other direction, or when the current is really small, or when the current is really big. So if we calculate them over a large range of currents, the conclusions are more likely to be valid. So how many indicative points do we have? We have this one. How we're going to measure voltmeter is a mark. How we're going to calculate resistance is another point. How we're going to change the resistance and why we're doing this. And this last point about making sure we calculate the values of a large range. So we have 5 indicative points, which means we're likely to get 4 marks. The students' results are shown in figure 6. We can see there's a graph of resistance against current. Describe how the resistance of the filament lamp changes as the current through it increases. We can see from the graph, as current increases, resistance also increases. This is a 1-mark question, so that's all we need to write. Use figure 6 to estimate the resistance of the filament lamp when a current of 0.1 amp passes through the lamp. So the line on the graph doesn't quite reach 0.1 amps, so you need to carefully extend the line following the trend. So you can see at 0.1 amps, the resistance is approximately 6.5 ohms. Because you're drawing your own line, there's a range of acceptable answers from 6.3 ohms to 6.9 ohms. The current potential difference graphs of 3 components is shown in figure 7. Use answers from the box to identify each component. From graph A, we can see that this component starts off being a ohmic component, as current starts off being directly proportional to potential difference. But as the potential difference increases further, we can see that the gradient changes. What does this tell us? So we know that the gradient of a graph is y divided by x, so in this case it's current divided by potential difference. We know that resistance is voltage divided by current, so we can see that the gradient of this graph is 1 divided by r. So as the potential difference increases, we see that the gradient decreases. This means the resistance increases. So this is the current potential difference graph for a filament lamp. This happens because as the potential difference increases, the temperature increases, so the resistance increases. In graph B, current is directly proportional to potential difference, so it's an ohmic conductor. The only ohmic conductor on our list is a resistor at constant temperature. In graph C, we can see that the current can only flow in one direction. No matter how high the potential difference is in the reverse direction, the current is 0. We can also see that in the forwards direction, the gradient is relatively high, so the resistance is relatively low. We should be able to recognize these characteristics from the IV graph of a diode. A student rubs an acetate rod with a cloth. Figure 8 shows the charges on the acetate rod and the cloth before and after rubbing. Explain how rubbing an acetate rod with a cloth causes the rod and cloth to become charged. So we can see before rubbing there's approximately equal amounts of positive and negative charges on both the rod and the cloth, whereas after the rubbing there are fewer electrons than before on the rod and more electrons than before on the cloth. So that gives the cloth an overall negative charge and the rod an overall positive charge. We can actually see that electrons have moved from the rod to the cloth. The question asks how the rod and the cloth become charged. So it's this process of the movement of electrons that we need to explain.
We should start off our explanation with what causes the movement of these electrons. We saw in the question that it's the rubbing that causes this, and it's actually the friction. So we should start by saying that the friction between the rod and the cloth causes electrons to move from the acetate rod to the cloth. So now there are more electrons than positive charges on the cloth and fewer electrons than positive charges on the rod. So the net charge on the cloth is now negative, and the net charge on the rod is now positive. This question is marked based off indicative points. We get one indicative point for saying the friction between the rod and the cloth, another for the movement of electrons, another for the direction of the electrons, so from the rod to the cloth, and then two more for saying the net charge on the cloth is now negative and the net charge on the rod is now positive. After charging them, the student moves the acetate rod and the cloth closer together. Which statement is correct? Is it there is no force between the acetate rod and the cloth? Is it there is a force of attraction between them? Or is it there's a force of repulsion between them? So the key fact we need to remember for this question is that like charges repel and unlike charges attract. We know from the previous question that after rubbing them together, the rod has a positive charge and the cloth has a negative charge. So these charges are unlike, which means they're going to attract. So the correct answer is that there's a force of attraction between the acetate rod and the cloth. Give a reason for your answer. Well, this is because unlike charges attract. Figure 9 shows a Van de Graaff generator which is used to generate static electricity. We can see there's an earth sphere, a metal dome and an insulator. The longer the Van de Graaff generator is switched on, the more charge is stored on the metal dome. Use an answer from the box to complete the sentence. The amount of charge on the metal dome is increased, which causes the potential difference between the metal dome and the earth sphere to either decrease, increase or stay the same. So the charge on the earth sphere is going to stay constant and the charge on the metal dome is increased. So the difference in charge is going to increase. So this means that the potential difference between the metal dome and the earth sphere will increase. When the potential difference between the Van de Graaff generator and the Earth's sphere is 60 kilovolts, a spark jumps between the metal dome and the Earth's sphere. The spark transfers 0.00025 coulombs of charge to the Earth's sphere. The equation which links charge, energy and potential difference is energy transferred equals charge times potential difference. Calculate the energy transferred by the spark. So we want to find the energy transferred in joules. So for that we need the charge in coulombs and the potential difference in volts. We are already given the charge in coulombs, but the potential difference is given to us in kilovolts. So we need to find that in volts. 1 kilovolt is 1,000 volts. So 60 kilovolts is 60,000 volts. That means the energy transferred in joules is going to be 0.00025 coulombs times 60,000 volts. This is 1.5 joules. So that's our answer. We get 1 mark for this line of working out and 1 mark for the final answer. Alpha, beta and gamma are types of nuclear radiation. Draw one line from each type of radiation to what the radiation consists of. So you have alpha, beta and gamma. So for this question you just need to remember the definitions. So alpha is made out of 2 protons and 2 neutrons. Beta is the radiation when a neutron changes to a proton and an electron. So it is an electron from the nucleus. And gamma radiation has no mass because it's a form of electromagnetic radiation. A teacher demonstrates the penetration of alpha, beta and gamma radiation through different materials. The demonstration is shown in Figure 10. Complete Figure 10 by writing the name of the correct radiation in each box. So Figure 10 shows that the radiation at the top has the greatest penetration power because it is stopped by 5 centimeters of lead, whereas the radiation at the bottom has the smallest penetration power because it only takes 1 sheet of paper to stop it. A radiation's penetration power is determined by how big and heavy it is. Large radiation will have lots of collisions with the atoms in the material, so will not penetrate as much. Alpha radiation is the biggest and heaviest because it's made up of 2 neutrons and 2 protons. And gamma radiation has no mass at all, so that's going to be the lightest. Beta radiation is made up of 1 electron, so that's going to be somewhere in the middle. That means alpha will have the lowest penetration power, gamma the greatest, and beta will be in the middle. Table 1 shows how the count rate from a radioactive source changes with time. Use Table 1 to calculate the count rate after 200 seconds. So for this question we need to understand what is a half-life. In this context, a half-life is the time taken for the count rate to halve. From the table we can see that the count rate halves from 400 to 200 in 80 seconds. And if we look again, after another 80 seconds, the count rate has halved again from 200 to 100. This means that the half-life is 80 seconds. So how do we find the count rate after 200 seconds? We can spot that 120 plus 80 is 200 seconds. If the half-life is 80 seconds, that means that the count rate at 200 seconds is going to be 141 divided by 2. This is equal to 70.5 or approximately 71. So the count rate after 200 seconds is equal to 71 counts per second. We get 1 mark for stating the half-life and 1 mark for the final answer. The half-life of the radioactive source used was very short. Give 1 reason why this radioactive source would be much less hazardous after 800 seconds. So if the half-life is very short, after 800 seconds that's going to be many half-lives. This means that the count rate will have decreased many times, so it's going to be much smaller than it was before. It's going to be much less hazardous because only a very small amount of radiation would be emitted. An electrician is replacing an old electric shower with a new one. The inside of the old shower is shown in Figure 11. The electrician should not change the shower unless he switches off the mains electricity supply. Explain why. To fix the shower, the electrician will have to touch wires with his hands. Maybe he'll be switching the wires about. You know that you should not touch things with electricity going through them because there's a risk of being electrocuted. So the electrician needs to switch off the mains electricity supply because if he touches a live wire, he may be electrocuted. Saying he may be electrocuted or he may get an electric shock is 1 mark, and saying this might happen if he touches a live wire is the 2nd mark. The new shower has a power output of 10,690 watts when it's connected to the 230 volts mains electricity supply. The equation which links current, potential difference and power is current equals power divided by potential difference. Calculate the current passing through the new shower. Give your answer to two significant figures. So we want to find the current, and we're given the equation for current here. But do we have all the information we need? We have the power, that's here, 10,690 watts, and we also have the potential difference. We know that this is potential difference because it has the unit volts, which is the unit potential difference. So to find the current, we have all the information we need and we can plug it into the equation. So the current is 10,690 watts divided by 230 volts. If we want the current in amps, watts and volts are the correct units to use. If we type this into our calculator, we get an answer of 46.478 continues on amps. The question asks us, however, to give our answer to two significant figures. This is 4 is the first significant figure and 6 is the second significant figure, so we need to get rid of all the rest of them. 4 rounds down, which means our answer to two significant figures is 46 amps. We get 1 mark for identifying which equation to use, 1 mark for plugging in the correct values, 1 mark for finding the answer we get on our calculator, and then the final mark for rounding to the correct number of significant figures. The new shower has a higher power rating than the old shower. How does the power of the new shower affect the cost of using the shower? Give a reason for your answer. So the power rating, or the power, is a measure of the energy used divided by time. So that means a shower with a higher power rating in the same amount of time as a shower with a lower power rating is going to use more energy. Energy costs money, so a higher power rating means more cost. So we can say that a higher power rating means that more energy will be used per unit time, meaning it will have a higher cost. You get 1 mark for saying it will cost more, and 1 mark for saying that's because it will use more energy. Figure 12 shows a balloon filled with helium gas. Describe the movement of particles of helium gas inside the balloon. So this question is asking us to describe the movement of particles in a gas. You might have memorized these properties, but if not, you can use a diagram to help. The arrows on the blobs represent the movement of particles. One thing you might notice about the arrows is that they are a range of different sizes. This represents how they are moving at a range of different speeds. Another thing you might notice is that the arrows are pointing in lots of different random directions. This represents how the particles are moving in different directions. This question is worth 2 marks, and just from using the diagram we have 2 points about the movement of particles in a gas. We can say that the particles are moving with a range of speeds in a range of different directions. The range of speeds is 1 mark and the range of directions is the second mark. What is the name given to the total kinetic energy and potential energy of all of the particles of helium gas in the balloon? Is it external energy? I've never heard of that before, so it's probably not that. Is it internal energy? Internal energy is the total energy in the kinetic energy store and potential energy store of particles in a substance. This does match our definition, so I think that's the right answer, but I'll check the last one just to make sure. Is it movement energy? Movement energy is an informal term for kinetic energy, so that's not the answer. And this is the correct answer. Write down the equation which links density, mass, and volume. This is just an equation you need to remember, and it's density is equal to mass divided by volume. Sometimes it's easy to remember that the unit for density is normally kilogram per meter cubed, and this is the unit for mass, and this is a unit for volume. So it's another way to remember that density is mass divided by volume. The helium in the balloon has a mass of 0.00254 kilograms. The balloon has a volume of 0.0141 meters cubed. Calculate the density of helium. Choose the correct unit from the box. So in our last question, we found out that density is mass divided by volume. We are given both mass and volume in the equation, so we can say that density is 0.00254 kilograms divided by 0.0141 meters cubed. If we type this into our calculator, we get a value of 0.1801418, and it continues on. In the question, both the values we're given are given to 3 significant figures. This means we should give our answer to 3 significant figures. That means our answer is 0.180. But how do we find the units? So the value is the mass divided by the volume. So the unit is also the unit for mass divided by the unit for volume. So it's kilograms per meters cubed. We get 1 mark for this calculation here. We get 1 mark for our value and 1 mark for our unit. Scientists sometimes replace one scientific model with a different model. For example, in the early 20th century, the plum pudding model of the atom was replaced by the nuclear model of the atom. Explain what led to the plum pudding model of the atom being replaced by the nuclear model of the atom. So you should know that the plum pudding model was replaced by the nuclear model because of the Rutherford scattering experiment. This question is worth 6 marks, so we need to explain the process of the plum pudding model and what led to the plum pudding model changing because of the Rutherford experiment. So, to explain this process, what do we need to include? Well, first of all, we need to explain what was the plum pudding model. We also need to explain what was the experiment and how did they do it. We then need to explain the observations from the experiment. And then we need to describe the findings that came because of these observations. So the plum pudding model was what they thought that atoms looked like in the early 20th century. They thought that it was a ball of positive charge with negative charges spread throughout it like plums in a plum pudding. So in the plum pudding model, mass and charge are evenly spread throughout the atom. Next we need to say which experiment meant that the plum pudding model changed and how they conducted this. So it was Rutherford's alpha scattering experiment that meant that the plum pudding model had to be replaced. And he did this by firing alpha particles at a thin sheet of gold foil. So next we need to describe the observations of the experiment, so what they noticed when they fired alpha particles at gold foil and what these observations led to, what changes they led to. So you need to remember there are 3 observations and 3 changes that these observations led to. The first one is that Most of the alpha particles actually pass straight through the gold foil. This shows that most of the atom is actually made up of empty space. The second one was that some particles were deflected. This shows that there is a charged nucleus. So the third and final point was that a few alpha particles bounced straight back, showing that the nucleus has a large mass. Altogether, these show that the observations contradict the plum pudding model, so it was not correct and had to be replaced. This question is 6 marks, and to get 6 marks you need to have a detailed and logical explanation. You need to be clear and coherent, and you need to demonstrate a deep knowledge. You also need as many indicative points as you can. We have one indicative charge saying that mass is spread throughout the atom, and a second from charge. You get a point for identifying the Rutherford experiment, and another for describing it. Then you get a mark each for the 3 observations. So that's the first observation, the second observation, and the third observation, and then more indicative points for what these observations showed. So most of the atom is empty space, that there's a charged nucleus, and the nucleus has a large mass. The national grid ensures that the supply of electricity always meets the demand of the consumers. Figure 13 shows how the output from fossil fuel power stations in the UK varied over a 24-hour period. You can see that there's the total power output on the y-axis and the time on the x-axis. Suggest one reason for the shape of the graph between 3 PM and 6 PM on Monday. 3 PM is here, and 6 PM is about here. You can see that there's a sharp increase in the total power output. But why is this? Why is there a sharp increase in the power output between 3 PM and 6 PM? So if you think about what normally happens during this time on a Monday, normally it's the time where people start getting back from school and work. They might have a cup of tea with the kettle on, they might start making dinner, turn the telly on, so maybe that's why the power output increases. It's because people are coming home from school and work. Gas-fired power stations reduce their output when demand for electricity is low. Suggest one time on figure 13 when the demand for electricity was low. So if we look back at the graph, you can see one point where the demand for electricity, or the total power output, is low is here. If we draw that back onto the x-axis, we can see that this is this time here. So demand for electricity was low at this time, or midnight. The national grid ensures that fossil fuel power stations in the UK only produce about 33% of the total electricity they could produce when operating at maximum output. Suggest 2 reasons why. So we know that in the UK we have more than enough electricity than we need. We never go to switch on a light and there isn't any, so we must have enough. That means that 33% is enough for a whole country. But you might think, well, why don't they just produce 100% anyway? That's because producing more electricity than we need would unnecessarily harm the environment. On top of that, only using 33% means that there's a lot of spare capacity for if there's an emergency. For example, if a power station has to shut down, it doesn't mean that the whole country's electricity gets shut off, because that would be incredibly dangerous. Instead, they'd have just lots of other power stations that could take over. So it means there's spare capacity if a power station shuts down. A student investigated how much energy from the sun was incident on the Earth's surface at her location. She put an insulated pan of water in direct sunlight and measured the time it took for the temperature of the water to increase by 0.6 degrees C. The apparatus she used is shown in figure 14. You can see there's the apparatus as described. Choose the most appropriate resolution for the thermometer used by the student. So resolution is the smallest change in a value that can be detected. A thermometer of resolution 0.1, 0.5 and 1 degrees would look like this. We know from the question that they're trying to find a temperature change of 0.6 degrees C. On both the thermometers with a 0.5 degree Celsius resolution and a 1 degree Celsius resolution, you cannot exactly measure 0.6 degrees C, so that they would not be appropriate. So the most appropriate resolution would be 0.1 degrees C. The energy transferred to the water was 1050 joules. The time taken for the water temperature to increase by 0.6 degrees C was 5 minutes. The specific heat capacity of water is 4,200 joules per kilogram degree C. Write down the equation which links energy transferred, power and time. So the definition of power is the energy transformed or transferred per second, and the unit is the watt, which means that power is energy transferred divided by time. Calculate the mean power supplied by the sun to the water in the pan. So we know from the last part that power is energy transferred divided by time. We are given both the energy transferred and the time in the question. The energy transferred is given in joules, which is the correct unit for this equation, but the time is given in minutes. And when we use time, we normally measure it in seconds. 5 minutes is 5 times 60, because there are 60 seconds in a minute, so 5 minutes is 300 seconds. So we can plug these values into our equation. So it's 1050 joules divided by 300 seconds, which is 3.5 watts. You get 1 mark for this calculation and 1 mark for the final answer. Calculate the mass of the water the student used in her investigation. Use the correct equation from the physics equation sheet. So we need to find an equation that involves mass, as well as information that we're given in the question. In the question we're given energy transferred, time, change in temperature and specific heat capacity. So if we look at the physics equation sheet, what equations use only these values? The equation we will find is energy transferred equals mass times specific heat capacity times change in temperature. We can rearrange that to get mass, which is energy transferred divided by specific heat capacity times change in temperature. We can plug in the values from the question. Energy transferred was 1050 joules. Specific heat capacity was 4,200 joules per kilogram degrees C, and change in temperature was 0.6 degrees C. If we plug these values into our calculator, we get an answer of 5/12, which to 3 significant figures rounds to 0.417 kilograms. We get 1 mark for identifying the right equation as well as substituting in the correct values. We get 1 mark for rearranging the equation, and the final mark for the final answer. The student's results can only be used as an estimate of the mean power at her location. Give one reason why. So the mean power at her location is the energy transferred to her location divided by time. However, what she calculated was the energy transferred to her location that is used to heat up the water divided by time. She calculated this using E equals mc delta theta. These two values are not the same because not all energy is going to be transferred to the water. Nearly all of it will be, but not all of it. For example, some energy will heat up the metal pan. Another similar reason that you could give is that some energy will be transferred to the surroundings. A student investigated the efficiency of a motor using the equipment in figure 15. In figure 15 you can see a weight being lifted up by a string attached to a pulley and a motor. He used the motor to lift a weight of 2.5 newtons at a height of 2 meters. He measured the speed at which the weight was lifted and calculated the efficiency of the energy transfer. He repeated the experiment to gain two sets of data. Give one variable that the student controlled in his investigation. So controlled means kept constant. So we need to find which variables were the same every time. So he said this sentence says he used the motor to lift a weight of 2.5 newtons, a height of 2 meters. So that means every time he did the experiment, he used a weight of 2.5 newtons and a height of 2 meters. So weight and height are both control variables. You only need to write one of these to get full marks. Give two reasons for taking repeat readings in an investigation. So we often take repeat readings in an investigation and it's for the same reasons every time. The first reason is that you can identify anomalies. If you take lots of readings and there's one that's completely different from the rest, you'll know that that's an anomalous result. Whereas if you only take one and you get an anomalous result, you won't realise. So that's a really good reason for taking repeat readings. Another reason for repeating reading is so you can calculate a mean. A mean, or an average, reduces the effect of random errors. Figure 16 shows a graph of the student's results. We can see there's efficiency on the y-axis and speed on the x-axis. Give two conclusions that can be made from the data in figure 16. So to answer this, we can look at the shape of the graph and write down the two things that we notice. So the first thing we'll notice is that there's a positive correlation because the line is pointing in this direction. So that means that as speed increases, efficiency also increases. The second thing we'll notice is that instead of forming a straight line, the points start to plateau off like this. Why does it start to curve like this? Well, if it was a straight line with efficiency on the y-axis and speed on the x-axis, we know that if there's infinite speed, there's going to be infinite efficiency. But we know that this can't be true because efficiency can't be over 100%. So the graph makes this shape because the graph tends towards a constant value. So this first point gets us the first mark, and this second point gets us the second mark. Give the main way that the motor is likely to waste energy. So we know that the motor is supposed to pull up the weight by moving. So the motor is going to spend energy. So the motor is going to use energy so that it moves and it can lift up the weight. So this is not wasted energy. We also know that when things move, they normally get hot. And we don't want the motor to get hot. So this energy is wasted. So the motor will waste energy by heating the surroundings. When the total power input to the motor was 5 watts, the motor could not lift the 2.5 Newton weight. State the efficiency of the motor. If the motor could not lift the 2.5 Newton weight, it means the weight did not move at all. So this means that the work done is going to be 0. Power is work done divided by time, and 0 divided by anything is 0. So the output power is also going to be 0. Efficiency as a percentage is output power divided by input power times 100. So the output power is 0, the input power is 5, times 100 is 0. So the efficiency is 0%.